So let's get going. It's my pleasure today to introduce Professor Robert Fovell, who's coming down to us here from the University of Albany, where he's a full professor there in the Department of Atmospheric and Environmental Sciences. Rob's specialty, as you'll be hearing about today, is on mesoscale and convective meteorology, using both observations and especially models to probe into these storms and so forth, and learn a lot about the physics and so forth. Just to give a little bit of background on Rob, he received his PhD from the University of Illinois in 1988. And from 1991 to 2015, for 25 years, he was at the UCLA, Los Angeles there, where he worked out from assistant to full professor, and even served as chair for a few years, I believe. Other recognitions, in 2012, he received the American Meteorological Society Distinguished Teaching Award, which is only given to one faculty member or instructor around the country. So he's an exceptional teacher. In 2013, he became a fellow of the AMS, American Meteorological Society. He's currently an editor at JAS, Journal of Atmospheric Sciences. So he moved to Albany in 2015, get away from LA a little bit. So it's nice to have Rob in the neighborhood, at least upstate. So let's welcome Rob here today.
All right, thank you very much. Can you hear me in the back? Okay. I tried to move as far from LA as I could, so that took me to Albany. Okay. So I'd like to talk to you today about some research we've been doing over the past few years regarding how model physics controls tropical cyclone structure. The rough outline here is I'll give you some background and motivation, and then the first part of this will discuss cloud-radiative forcing and its influence on tropical cyclones. Cloud-radiative forcing, which I'll call CRF, is the interaction of hydrometeors with long-wave and short-wave radiation. Then we'll talk about the planetary boundary layer and how the, mixing in the boundary layer controls tropical cyclone structure, and then I'll bring this thing to a conclusion. Okay? So regarding the background, I'd like to start with one of my favorite quotes, which is, make things as simple as possible, but no simpler. Okay, that's the way I try to approach research. Basically, you look at things are so complex, so I try to get things down to its simplest parts, but again, no simpler. Interestingly enough, this is attributed to Albert Einstein, but it is not clear that Albert Einstein actually ever said this. He conveyed this thought in a more complex fashion, and ironically, someone else had to make that simpler. So, so basically, back in the early 2000s, I think it was around 2003, 2004, WRF version 2 came out, and I started using WRF. It finally became usable to me. Actually, let me just admit, I finally managed to get it compiled. And I was, at the time, I was studying things like squall lines and sea breeze circulations, but I wanted to study something relatively simpler, and I thought tropical cyclones are fairly simple. They just look like little bullseyes or targets on low-resolution simulations, so I started with that. And I quickly noticed that if I manipulated things like the cumulus parameterization and the microphysics parameterizations, I could get very different intensities and tracks from those simulations. And I thought that was fascinating. I wanted to know how, and I wanted to know why. But I was simulating things like Hurricane Rita and Hurricane Katrina, and they form in very complex environments. There's vertical wind shear, there's wind, there are temperature gradients, there's land and sea, there's sea surface temperature variations. So in the spirit of trying to make things as simple as possible, I took the operational version of the WRF model and I systematically simplified it. I removed all of the land. I initialized the simulation with a single sounding. It was calm, no wind, no vertical wind shear. And I initialized the simulations with a tropical cyclone, and I looked at how microphysics influenced the tropical cyclone. So that's what you're seeing here. This is a simulation from what I call a semi-idealized experiment. I call it semi-idealized, not idealized, because at the time, idealized tropical cyclone simulations were very different from operational ones. They didn't have boundary layers. They didn't have things like surface layers. They didn't have all sorts of other physics that basically operational models would have. They usually neglected radiation as an example. So these are tracks from a 3 or 4 day simulation. It had 3-kilometer resolution using the WRF ARW, but no land. Now you may have noticed I sketched on a perhaps familiar section of the Gulf coastline, okay, mimicking Hurricane Rita's landfall, just to give you a sense of scale. But there's 7 different microphysics schemes here. They all started with the same initial condition, but over the first day and a half they start differentiating, and then they start having different movements, and they have different landfalls if there were land. One of these simulations, the one in red here, manages to break out of the pack and move much faster than any of the other simulations, but even the other ones are varying in terms of direction in ways that are important to a 2 or 3 day forecast. It basically would be a different set of people that you would be warning in this particular case. Okay? So the reason why this appears to work this way is microphysics are producing storms that are different. Even microphysics schemes that are ostensibly similar, they may have the same number of species. They're all trying to simulate things like free-floating cloud ice, low-density snow, medium-density graupel, but they produce different amounts of various kinds of hydrometeors that results in different patterns of diabatic heating, different tangential wind profiles, different asymmetry patterns, different intensities and different motions, which are basically seen graphically there. Okay? So as an example of this, the figure at the right now, the horizontal axis is radius from the center of the storm out 800 kilometers. The vertical axis is the 850 millibar wind speed that I averaged over one full 24-hour period and also averaged azimuthally around the storm for 3 of these simulations. And you can see that, well, there are different intensities at the radius and maximum wind. The winds in all 3 cases decrease towards the outer radius, but the wind speeds are different, okay? The wind speeds are stronger in one case, they're weaker in another case, and even if that doesn't seem very important to you, the difference may not seem all that relevant, it's actually a big difference. I'm showing you the difference, or basically the difference in what we call the radius of gale force winds. That's 34 knots, or about 18 meters per second. And there's a 70% difference in storm size going from the smaller to the larger one. That's important for motion, it's important for storm surge, it's important for who gets warned and evacuated and why. So these are actually very relevant differences. So here's that picture I just showed you of the magnitude of the winds in the outer core out 400, 500, 600 kilometers actually participates, amongst other things, in controlling the motion of the tropical cyclone. That was demonstrated in this classic experiment from 1989 by Fiorino and Ellsbury. This was actually a very simple model in which they basically initialized a tropical cyclone with 3 different radial wind patterns that look like this, that differ with respect to the wind speed beyond 300 kilometers from the storm center. And those 3 cases labeled A, B, and C produce very different tracks, as shown at the lower right. Okay? So one storm with the stronger winds at outer radius propagates faster towards the northwest, and slower propagation more towards the north for the storm with the weaker winds at outer radius. So it's actually very similar to what's going on here. So that's why the winds at outer radius are important. Yes, sir?
How do you know that it's not just variability? If you initialize it with just different noise, pretty large uncertainty at the beginning, how do you know that it's microphysics?
Okay, well, you can ask me that at the end, okay? Okay, so different microphysics schemes, even schemes that are relatively similar. I know there's a lot of people who understand microphysics here, like producing cloud ice, snow, and graupel, produce different amounts of different of these species because they have different assumptions regarding accretion efficiencies and things like that, drop size or particle size distributions. This is just an example of that. These are 4 different microphysics schemes. The vertical axis is the fraction of total ice in a certain part of the tropical cyclone. This is cloud ice. some schemes produce relatively little cloud ice because they move mass of hydrometeors more efficiently to snow or graupel. Others produce lots of cloud ice. And there's a great deal of uncertainty there. We don't really know which one is more important, but or which one is more realistic, but it is making a difference here because I'm showing you it's making a difference at the left, okay? So in the spirit of trying to make things as simple as possible, I'm still going through my experiment trying to find things that I can neglect, okay? Can I turn this off? Can I simplify that? So one of the things I identified was to turn off the cloud-radiative forcing, okay? The cloud-radiative forcing is how ice crystals or snowflakes or graupel particles interact with long-wave and short-wave radiation, okay? So the way I did that, so I did this experiment in which I turned off the cloud-radiative forcing, which is a fancy way of saying I made the clouds transparent so the clouds were no longer cloudy, okay? And in that particular experiment, which you see at the right, all of the variability due to microphysics went away. These microphysics schemes are still producing different amounts of different species of hydrometeors like cloud ice and snow, but it doesn't matter anymore. It doesn't matter anymore to the motion. It didn't matter anymore to the structure. There were 7 copies, virtually identical copies of the same thing. So it wasn't the microphysics per se, it was how the microphysics was interacting with radiation. And it mattered because microphysics interacts with cloud ice differently than with snow. And it interacts with snow differently than with graupel or cloud water or raindrops and stuff like that. So this was a very interesting result. And so it launched me off into an investigation of trying to understand how and why the cloud-radiative forcing influences the tropical cyclone structure. Before I can explain why, I have to understand how, okay? So now I'm going to shift models. I'm not using WRF A or W anymore. I'm using HWRF. I'll explain why I'm using HWRF later on. This is temporally averaged lower tropospheric vertical velocity over a 400 by 400 kilometer section centered on the storm. It may not look very much like a tropical cyclone to you because this is not condensation. It is vertical velocity. It's vertical velocity averaged from the sea surface up to 500 millibars and also averaged over a full diurnal cycle of 24 hours. Okay? So what we see here is intense rising motion near the center of the storm and the eye wall. There is something that looks like a principal rain band out at outer radius, and there's a lot of convective activity also at outer radius. If I now azimuthally average around this, I could produce a structure that looks like this. The horizontal axis is about 350 kilometers out from the center. The vertical axis is 18 kilometers from the sea surface to the top of this particular figure. The colored field is the radial flow. Blue is in, red is out, so we call this the secondary circulation. The wind comes in here in the boundary layer, rises, and then goes out in the upper troposphere. The contours superimposed are the tangential velocity, so that is the cyclonic flow into the page. I am highlighting one particular contour here, the 20 meters per second, and I chose that because that is close to the radius of gale force winds, 34 knots or about 18 meters per second. So what I see here is this particular structure. If now I look at the condensation field instead, this is a log2 scale, but we're seeing where the cloud water, the ice crystals, and the other condensate particles are coming together. The condensation field is largest in the eye wall, but it extends quite a bit out radially outward. Superimposed on this is the net radiative forcing over a 24-hour period. We see that there is cooling along the cloud top. That's primarily due to long wave cooling the space. And then there is warming within the cloud that is much smaller in magnitude, okay? This is net radiative forcing over a 24-hour period, but actually that's the sum of long wave and short wave radiation, so let's separate those two. So at the top is the long wave forcing. Actually, the cooling is as large as 13 Kelvin per day. You know, that may seem like a large number, but it's actually fairly small because you can get 13 Kelvin per 10 or 20 minutes from microphysics diabatic forcing in the eye wall. Okay, so actually these diabatic forcings associated with the long wave cooling and the short wave absorption are actually fairly small. And the short wave is actually opposing the long wave. It's basically 6K per day of warming at the cloud top, but the sun is only up about half the time in these simulations, so that's why the net radiation is cooling at the top of the cloud. Okay? And notice the sunlight doesn't get very far into the cloud, so it's not reaching the middle to lower troposphere. So the warming that is occurring, this weak warming within the tropical cyclone central dense overcast, is primarily long wave emission. Okay? So I showed you this figure at the left before. This was tropospheric averaged vertical velocity. For the simulation I call CRF-on because I am allowing hydrometeors to participate with radiation. And the figure at the right is the CRF-off counterpart. So my clouds are not cloudy. And I can see immediately that there is a big difference, particularly at outer radius, that outer ring there, where there's a lot less red. Okay, so there's less convective activity at outer radius. Okay, this is the average 10-meter winds. The horizontal axis is radius from the storm center out to 240 kilometers. The vertical axis is the 10-meter wind speed. And so I'm showing you that the radius of 34-knot winds is about 180 kilometers or so. That's the CRF-on simulation. The CRF-off simulation, other things being equal, produces a tropical cyclone that is much narrower. Okay? It's actually 74% smaller, going from the smaller to the larger value. So that's a significant amount that influences things like storm speed. Can you hold on a sec? Okay. It affects things like the storm motion. It affects storm surge and other quantities like that. It's not just at the surface. The storm isn't just different size at the surface, but throughout the entire troposphere. Horizontal dimension out to 350 kilometers, vertical axis up to 18 kilometers, CRF-on, CRF-off. If you just look at the 20 meter per second contour, you can see it's significantly more radially expansive in the simulation that has the cloud-radiative forcing on. CRF-off doesn't mean I turned off radiation. It means I just turned off the participation of hydrometeors with radiation. It still has the clear sky long wave and short wave components. Now I'm going to subtract these two. Okay? So you can see that there's a difference in the tangential wind field, but there's also a big difference in the radial flow as well. Stronger radial flow in the CRF-on case, stronger outflow in the upper troposphere, stronger flow into the page. Okay? And the same thing is true of the condensation field. CRF-on at the top, CRF-off, this is clear sky forcing only. So when I subtract the two of them, I can see there's more condensation out to a greater radius. Okay, in the CRF-on case, there's greater convective activity at outer radius. This may seem strange here to see this blue colored here because I'm subtracting two fields that are positive definite, but it's because there's an eye size difference. The eye here is narrower for CRF-off than for CRF-on. And so when I subtract the two, there's a negative difference in the condensation field. Okay? So what is happening here, I'll explain this in a little more detail later, but the consequence is there's more convective activity at larger radius in the simulation with cloud-radiative forcing. And so that convective activity is creating condensation, it's creating precipitation, it's creating diabatic forcing. Okay? Okay, so let me recap what I've shown you. The tropical cyclones with cloud-radiative forcing active have wider eyes, broader tangential wind fields, stronger secondary circulations, and more radially extensive convective activity. These simulations were made using the HWRF model, but I get basically very qualitatively similar results from WRF ARW. Okay? So at this point, I'd like to pivot to explain why the cloud-radiative forcing influences the size of the storm, not just near the sea surface, but throughout the entire troposphere. For this, I'm going to shift to an axisymmetric model because it's a lot easier to manipulate, to do to try to do the experiments that I'm going to demonstrate here. Okay? So I'm going to run these simulations for 12 days, and what I'm going to show you is average between days 9 and 12. Okay? What you're looking at here is a movie loop of the condensation field, which is color shaded, and the net radiation field, long wave plus short wave, which is contoured, over a 3-day period from the axisymmetric simulation. Okay? So you are seeing basically the combination of long wave and short wave. Each frame is an hour. Okay? So what you're immediately perceiving, I hope, is that there is a lot of variability between hours and amongst hours for the simulation. The storm doesn't look the same from hour to hour. It's growing larger, it's growing smaller. The cloud-radiative forcing field is responding to where the clouds are at a particular time because it's related to the hydrometeor relationship with radiation. Okay? If you're a sharp eye, you can see there's definitely a diurnal cycle. The magnitudes of these things, the width, the depth, these things are varying over a 24-hour period amongst other frequencies. But if I took all of these figures you're seeing and I averaged them together, it would look like the top panel here. Okay? So the horizontal axis is 300 kilometers. We're 18 kilometers deep. The color shading is, again, the condensation field. And we are seeing the cloud-radiative forcing averaged over several diurnal cycles. Okay? You see the cloud top cooling. You see warming, which was primarily long wave within the storm. This is for CRF-on. This is CRF-off. And here's the difference field. So I'm showing you this for several reasons. The first one is I'm getting very similar results from the axisymmetric simulations that I showed you from the more complex three-dimensional simulations. And I'm going to try to exploit this in a way that's much easier to do in an axisymmetric model than in a 3D model like WRF or HWRF. Okay? So what I'm going to do is I'm going to take the cloud-radiative forcing field from the upper left, which I told you varies from hour to hour because of the cloud changes its shape and locations, and also does not look like this immediately because it takes several days for the tropical cyclone to even form in an axisymmetric model. And I'm going to take this average field and I'm going to impose it on this simulation as an external forcing. Okay? So I'm asking the question, is interactive cloud-radiative forcing necessary? Is the diurnal cycle crucial? Notice I'm not asking, is the diurnal cycle important or relevant? I'm asking, is it a difference that makes a difference? Okay? So I'm going to take this field, which does not look like this at any instant of time. I'm going to impose it on this simulation, and I'm going to call that simulation CRF fixed. Okay? So that forcing field looks the same at every time step. I turn it on at the beginning of the model simulation. I hold it fixed through the entire simulation. The cloud-radiative forcing field is independent of clouds. It's independent of time. And the result looks like this. Okay? So now, if you compare the upper left and the upper right, you can see they're actually very similar. Your eye may first go to the blue contours, which are identical from left to right. Because at left, this is the time average field. At right, it's identical, but it is the external forcing that is held fixed at every time step. But the colored field, the condensation field, is also quite similar. There is much broader condensation field in the CRF-on simulation than the CRF-off. Okay? Now that I have demonstrated that I don't really need the diurnal cycle, or I don't need the cloud-radiative forcing to be specifically tied to when and where the clouds form, the next experiment I'm going to do is I'm going to separate the cloud top cooling from the within cloud warming. Because that's easy to do. I'm just going to apply part of that field and withhold the other part. So maybe think in your mind which of these fields you think is more important, but I'll show you the answer on the next slide. Okay? So now the middle panel on the right is the simulation in which there is just the cloud top cooling, the net forcing between long wave cooling and short wave absorption at the cloud top. And notice that had very little influence on the condensation field relative to CRF off. But the long wave warming within the cloud made a big difference. Okay, so it's that component of the cloud radiative forcing that is actually important here. So the cloud radiative forcing is largest in magnitude at the cloud top, but the cloud top forcing didn't matter. It's what's going on within the cloud, which is substantially weaker magnitude, that actually matters. And what is happening is what this long wave warming is basically bringing about convective activity at the outer region of the storm that didn't exist previously. So let me try to summarize this finding in this fashion. I have long wave warming through a deep layer of the cloud. The magnitude of the diabatic forcing associated with that is very small. 1 Kelvin per day at a max. Okay, that is not very much. Okay, but that diabatic forcing is persistent and it occurs over a deep layer. And as a consequence of that, it is encouraging gentle lifting within the storm. And that lifting is on the order of 1 kilometer per day, which is certainly very small relative to vertical motions within the eye wall of the tropical cyclone. But it is sufficient to lift air gently and effectively to saturation. Once you bring air to saturation, condensation happens and much larger diabatic forcing associated with convection occurs. So this weak forcing brings about this gentle lifting to saturation. Once saturation occurs, I have a much broader condensation field. I have much larger diabatic forcing over a much larger area. And it is the convective heating that broadens the wind field. Now, I also recognize that I've been insisting this without proving that to you. If I have convective heating, that's going to broaden the wind field because it's going to basically bring air in, up, and out, and then the Coriolis force is going to turn it. But that's been very well established in the literature, so I figured that I would skip that detailed explanation and just move on. Okay? Okay, so we published this in 2014. I was very happy with this study. I was very happy with the way the results came out and our interpretation. But after it appeared in print, I thought that there was a missed opportunity. There was a missed opportunity, perhaps, to demonstrate that the cloud radiative forcing was actively controlling the width of the storm, other things being equal in this particular simulation. So I thought of an experiment to test that the cloud radiative forcing was actively controlling the storm size. So this is the simulation I showed you before. Colored field is condensation. Contours are net cloud radiative forcing. The net cloud radiative forcing is fixed and externally imposed. But now I'm showing you over a much wider area. This goes out to 600 kilometers instead. Because I'm basically imposing this as external forcing, I can arbitrarily change its horizontal scale, making it 50% wider or 50% narrower. So at the top, it's the same field, but I've expanded it. At the bottom, it's the same field, but I contracted it. And now I'll show you, starting from the same initial time, running over the same period, what the condensation fields look like. When I restrict the cloud radiative forcing to a relatively narrow reach here, the storm never gets wider than the cloud radiative forcing field even after 12 days. But if I allow the cloud radiative forcing field to be radially more extensive, and remember it looks like that from the beginning, that's an externally imposed forcing, the consequence of that is the storm becomes much, much wider than it was otherwise possible. Okay, does this make sense? So what's actually happening in a real simulation in which the cloud radiative forcing is capable of changing with time, which is not here, the storm will look like this near the beginning of the simulation. The cloud field will not be very wide because the storm is not very wide. But the cloud field contains hydrometeors that are interacting primarily with long-wave radiation, causing this gentle lifting at outer radius, which is bringing air to saturation and provoking convective activity. Once the convective activity gets going, there is stronger outflow. The outflow extends over a greater depth or a greater radial extent. That outflow is also carrying hydrometeors. Those hydrometeors are carrying the cloud-radiative forcing because they are the mechanism of the cloud-radiative forcing. So as the cloud-radiative forcing field expands, the region of the gentle lifting expands farther outward, and so therefore there's even more convective activity producing more diabatic forcing, expanding the wind field. So we'll go from this to this to this as a function of time. Okay? All right, and those three simulations are associated with wind fields near the sea surface that are very, very different. Okay? So I showed you this previous. I'm going to shift back from the axisymmetric model to the HWRF model. I showed you that going from the CRF off to the CRF on, having the cloud-radiative forcing on makes a much wider storm, that has consequences for storm motion and storm surge, if not necessarily storm intensity. Now I'm going to show you what the operational version of the HWRF model, that's the red curve, was doing at the time that we started using the HWRF model. The operational version of the HWRF model did not have cloud-radiative forcing. Okay? In the operational version of the HWRF model, for years, the clouds were not cloudy. They were transparent to radiation. You may ask, why did that happen? And the answer was it was a bug. Okay? It was a bug and it wasn't caught. Well, it was caught by us. Okay? So let me recap here cloud-radiative forcing in HWRF. In our 2014 paper, we demonstrated that it was long-wave warming within the Anvil cloud that caused gentle ascent, primarily in the middle troposphere above the PBL, that enhanced outer convection and expanded the wind field. We also showed in that last experiment it was a positive feedback. Okay, so it actually actively determined how wide the storm can get. The operational HWRF model's radiation scheme was lacking effective cloud-radiative forcing at the time. That was a bug. So we communicated our findings to the HWRF developers. They said, thank you very much. We'll work on this. We provided a code that actually would work. They tested it, and it made the model forecast worse. Okay? So what happened was they fixed the bug. The clouds weren't cloudy anymore, but the skill scores went down. They went down in the Atlantic quite a bit. They went way down in the East Pac. The skill scores got so much worse that actually they did not fix the bug. That bug went unfixed for one full hurricane season, okay, with clouds that were not cloudy, because the alternative of fixing that bug made the model forecast worse. If you're an operational meteorologist, you know that the thing you're being judged on is how good your skill scores are, right? But can you imagine looking at that model day after day, knowing that there's this serious bug in there, and you can't fix it because it makes the model worse? Okay? Okay. I know what you're thinking. You're thinking why? And I'm going to explain it to you. Okay? So the next part of this talk is about how the boundary layer controls the storm size. I showed you that the cloud-radiative forcing really participates in controlling the size of the storm. But it's not going to shock you that that's not the only thing that influences how big the storm can be in a model. Another thing that does it is the PBL scheme. Okay? So I've shown you simulations from actually 3 different models so far, 2 versions of WRF. And I don't know if you know much about WRF or know about the history of WRF, but WRF ARW and HWRF, they may share 3 letters, but they're very, very different models. They have different histories. Someone can explain to you what the history of WRF ARW and HWRF is, and I'm not going to do it now. Okay? But basically, they're very different models. So the reason why I was using HWRF, I was very happy using WRF ARW, is I proposed to NOAA to study the influence of physics on storm sizes based on the results that I showed you at the beginning of this talk. And they said, I've got good news for you. We're going to fund your proposal. And the better news is you get to use HWRF. And I said, what? I've never used HWRF. I don't know anything about it. Hurricane. Yeah, HWRF, Hurricane WRF. Okay, so I said, okay, I started simulating tropical cyclones with HWRF. I simulated Ophelia, I simulated Earl, I simulated a bunch of other cases. But again, it's really complicated. And so to make things as simple as possible, but hopefully no simpler, I designed semi-idealized experiments in HWRF just as I did in ARW. And I ran those side by side. I crafted those simulations using the operational versions of those models, using different model physics that they were using in operations, but with the same initial condition, no ocean model, constant sea surface temperature, no wind, initialized with a single sounding, no land, okay? In order to see how those models from the same initial condition produced tropical cyclones. And they produce very, very different tropical cyclone intensity and structure and size in a way that was very perplexing, okay? Well, one of those reasons was the lack of cloud-radiative forcing in the HWRF radiation scheme. So we were able to basically get past that and understand that, but that wasn't the entire difference. Another major difference through our analysis we realized is that the magnitude and the depth of the boundary layer and the boundary layer mixing was very different between WRF ARW and HWRF, okay? Now HWRF was using a boundary layer scheme called the GFS scheme, okay? And actually it still is using a version of that. There are 14 different boundary layer schemes in WRF ARW, okay? But one of the popular ones and one of the oldest ones is a scheme called YSU. And actually the YSU and the GFS PBL schemes share a common history. They basically both evolved from these ideas that were published some years ago, okay, in this particular paper, okay? And so let me cut to the chase and tell you what the answer is. Basically, excessive mixing in the boundary layer in the HWRF model was essentially compensating for the lack of cloud-radiative forcing in the radiation scheme. That boundary layer mixing also controlled the storm size. As the boundary layer mixing got larger, the storm sizes got bigger, so that with the excessive mixing, when they fixed the radiation bug, the storms became monsters in size, okay? So basically, you know, this is the way models work, okay? You can't fix one thing without breaking something else, okay? And you know, that's just the way it works. You know, that's the way life works with models. Sometimes, particularly if you're an operational meteorologist, you see something that's broken and you try to fix it. So you start changing schemes, you start tweaking schemes, you start adjusting knobs, you start doing things like that. And when it works, and you're happy. But you may not necessarily have altered the right thing, such that when you fix something else that was broken, like the cloud-radiative forcing, that combined with the previous tuning sends you out of whack again, and that's basically what happened in this particular case, okay? So these are two simulations, one using the unmodified GFS scheme that HWRF was using, that's in red. The black line uses the YSU PBL scheme that many WRF ARW simulations use. There's a difference in storm size near the sea surface of 36%. That may not seem very large, but it is actually a serious difference, and it influences intensity, motion, storm surge, and everything else. So before I explain why those PBL schemes, which share the same grandparents, why they're different, I need to explain a little bit of what they have in common. These are schemes called KPP schemes, which stands for K-profile parameterization. I'm going to try to give you a little flavor, as simple as possible, but hopefully no simpler, of how these things work. Here's a model equation, du dt, so u is the zonal velocity. On the right-hand side, we're going to have a term that looks like this, the vertical gradient of an eddy mixing coefficient multiplied by the vertical gradient of the field that I'm working with. And Km, this eddy mixing coefficient acting on momentum, is what we're interested in this particular thing. Some boundary layer schemes explicitly predict that, by prognosing turbulent kinetic energy. What KPP schemes like GFS and YSU do is they assume basically a vertical structure of eddy mixing that looks like this. So it's basically parabolic in shape between the sea surface and the boundary layer depth h. It kind of looks like a question mark turned upside down, and it's controlled by this particular equation, okay? So in this equation, the left-hand side is the eddy mixing that's going to produce that figure there. K is a constant, U star is friction velocity, phi is a stability corrector. This is a constant. These come from the surface layer scheme. Z is just height. So the only thing for the PBL scheme to do is determine what the depth of the boundary layer is. That boundary layer is H. Once you have H, you have everything you need to draw that profile there. But how you choose H is the difference here. And what H, the boundary layer depth, turns out to be controls the magnitude, the shape, the depth, and the height of the maximum mixing, as I'll try to explain next. So this is a vertical model column. Basically, the way I tried to determine on a column-by-column basis where the boundary layer depth is I basically compute a Richardson number, a stability divided by a vertical wind shear in this case, and I compare it to a critical Richardson number, which I supply. So I first compute the Richardson number between the surface and the first model level up, and I compare it to my critical Richardson number value. If it exceeds my critical Richardson number, I'm done. That's my boundary layer depth. If not, I go up between the surface and the second model level, compute the Richardson number again, compare it to the critical value. If it exceeds it, I'm done. If I'm not, I keep going. But ultimately, at some point, I'm going to reach a point where the critical Richardson number is exceeded. And at that point, you draw a line and say, that's the boundary layer top. That's essentially the way that works. At this point, I have H, I know Z, I have these things from the surface layer scheme. Kappa is a constant. I have everything I need to draw this particular profile. So now I'm going to show you profiles that come from time and azimuthally averaged profiles from the GFS and the YSU schemes. The GFS scheme produces a relatively large amount of mixing because its diagnosed PBL depth is high. The YSU scheme uses a different critical Richardson number, and as a consequence, it produces a PBL depth that is much lower and a mixing that is much smaller. The shapes of these profiles within the PBL is the same because it's controlled by that equation I showed you. But the difference is the boundary layer depth, and the boundary layer depths are different because they choose different critical Richardson numbers, okay? So if you go through the papers over the years, you'll see that one of the ways that these PBL schemes diverged is they changed their idea of what the critical Richardson number should be in various conditions. And so one chooses 0.25, and the other, when the surface layer is unstable, chooses a critical Richardson number of 0, okay? So that's not all the difference, but I can demonstrate that it's part of the difference and a large fraction of the difference by rerunning the YSU scheme with the same critical Richardson number that the GFS scheme uses, okay? So as I said, it's not all of the difference, but if I choose a larger critical Richardson number, you get larger boundary layer depths, you get greater mixing, and the height of the maximum mixing is shifted upwards from the sea surface more into like 500 meters above the sea surface, okay? So let's compare these two, which are the same scheme, but just differ by the critical Richardson number. We're looking at 240 kilometers by only 3 kilometers deep. The colored field is water vapor. The redder, the more moist in absolute humidity. You see the absolute humidity is largest near the center of the storm. It decreases radially outward. It decreases very rapidly upward. But if you compare the left and right panels, they may seem fairly similar to you, but they're actually different in an important way. But first, I'm going to show you what the eddy mixing applied to the water vapor field looks like. It's very different from one side to the other. Much larger magnitude at left, smaller magnitude at right, and a much smaller depth because the critical Richardson number is smaller, so the boundary layer depth is smaller. So now I'm going to subtract the two, okay? This is the colored contour here now. The blue contour is the difference in the eddy mixing fields between those two upper panels. And the color shaded field is the difference in the water vapor content. Actually focusing on that, we see that there's increased moisture near the top of the boundary layer in the simulation that has more mixing and a greater boundary layer depth, okay? And what is that increased moisture doing? That increased moisture is bringing air to saturation up from below. As it gets to saturation, convective activity ensues. The convective activity and the large diabatic heating associated with that broadens the wind field. So this is a completely independent and competitive way of controlling the width of the storm, not only at the sea surface, but also through the depth of the troposphere. Okay, so basically that's that little cloud, which is raining, is to show you that there's more convective activity in the simulation that has more eddy mixing. Okay, so let me summarize this. The GFS PBL scheme ostensibly, and I use ostensibly, that's a nice word, that's a GRE word, so you may have encountered it on the GRE exam. Ostensibly means that I think that the reason is that the mixing produced by the GFS scheme is too much. There's limited observations of the hurricane boundary layer, but the observations that I've been able to look at tell me that the mixing in the GFS scheme is way too much, okay? So that's controlled or reflects in large part the difference in the critical Richardson number that is used by these two ostensibly similar schemes. Some of this excessive mixing had been compensating for the missing cloud radiative forcing due to the bug in the HWRF radiation scheme. But when that bug was fixed, it basically revealed that the excessive mixing was producing storms that are way too big. I haven't shown you that actually mixing of momentum and temperature has a pretty small influence on the storm. It's the mixing of water vapor that's really important. And if you want more information on that, this paper had just appeared in the April issue, and that's what the second part of this talk was based on, okay? Now, one question you might have is, I showed you there's a really big difference between using a critical Richardson number that's relatively smaller and relatively larger. And a legitimate question is, which is correct? Okay? With all due respect, let me change the wording of that question and make it not which is correct, but rather which is less wrong. Does that make sense? Which is less wrong? You know, they're both wrong, but some things are more or less wrong than others, which reminds me of another of my favorite sayings: all models are wrong, but some are useful. Okay? All models are wrong, but some are useful. Okay? That's a good thing to keep in mind. Professor Box was actually thinking about statistical models when he wrote this, but it applies to dynamical models as well. Okay? Because models are filled with assumptions. And some of these assumptions work better with other assumptions, and some of these assumptions don't work very well at all. Okay? So let me synthesize this together. This is a depiction of a tropical cyclone cloud. Okay? You're going to have to use your little imagination here. My family is basically divided between artists and engineers, and I think it's pretty obvious which side of that line I fall on, okay? Because my artistic abilities are limited at best, okay? But this is radius in the horizontal, height this way. That's supposed to be a tropical cyclone cloud. This is the center of the tropical cyclone. The secondary circulation in, up, and out. I talked about that during this talk. And I also emphasized the role of long-wave cloud radiative forcing, which was causing weak, gentle lifting that is not very strong in magnitude, but it is extensive in terms of depth. It is persistent in terms of time, and that causes extra convective activity in the outer core, and that convective activity produces much larger diabatic forcings than the long-wave warming ever did, and that extra convective activity and the heat associated with that expands the tropical cyclone, okay? But wait, as they say on late night TV, there's more, okay? So this is the mixing field that is applied to moisture. And the mixing field is also lofting moisture towards the top of the boundary layer up from below, increasing the relative humidity at the top of the boundary layer, increasing the likelihood of provoking convective activity at outer radius. And so as a consequence, there are these two mechanisms for expanding the size of the storm, and expand it does. Okay? So let me close this with a very rapid summary. Model physics can profoundly influence storm size and represents a significant source of uncertainty. Radiation and microphysics and PBL vertical moisture mixing independently make storms wider. They can cooperate, they can compete, but they both work in the same way, by directly or indirectly inducing more convective activity over a wider region and the diabatic forcing that associates with that. Okay? The cloud-radiative forcing issue has been fixed as of the 2015 operational version of HWRF. I'm happy to say that we helped modify the boundary layer schemes such that they can now make their clouds cloudy. Okay? But I think this motivates evaluation of other PBL schemes and assumptions. Okay? And this research was supported by NOAA and NASA and the Developmental Testbed Center. So thank you for the invitation.
Just a live question here. So you show that when you fix the cloud-radiative forcing at different size, the storm actually sort of equilibrate to that size. But in nature, it's sort of not fixed. So what eventually fixed the size of the storm?
That's a very good question. And I'm not sure if I have a good answer for that. In the axisymmetric simulations, I showed you the tropical cyclones continually get wider because I showed you a positive feedback. Okay, and then a legitimate question is, when does the positive feedback end? A flippant answer would be when the typhoon reaches landfall. Okay, right? But let's say you had an ocean planet and you had the tropical cyclone was not going to move into a worse condition. My thinking was, that as the tropical cyclone anvil expands farther, each radial distance outward implies a much larger mass of clouds because you're moving outward in sort of like a polar coordinate system. And that as a consequence, that would have to basically slow down as some function of 1 over r or something like that. To kind of test that idea, I took the axisymmetric model and I ran it not for 12 days, but 120 days or 240 days, because people have been trying to do that in the literature, and I can understand why they're trying to do that, and I can respect that, but there are other issues that crop up once you run simulations that long that I find that I cannot come to a definitive answer to that particular question. But I think the bottom line is there's many different things conspire to produce what is the size of a particular storm. One is, what was its genesis size, right? If it started in the East Pac, it probably started with these little circulations near the ITCZ, and they tend to produce these small tropical cyclones. But in the West Pac, they start with these gyres, right? And these gyres tend to be much larger, so typhoons in the Western Pacific tend to be substantially larger than hurricanes in the Eastern Pacific. Well, if you're starting with a larger initial vortex, you're probably going to be larger throughout your life cycle. But given the same initial condition, there are many things that I think influence that, and I showed 2, okay? And the mixing from the boundary layer, I might add, also depends on how humid the boundary layer is. We basically were able to demonstrate we can shut off that influence on the storm size by just making the environment less humid. I don't think that's very surprising when you think about it. If there isn't very much water vapor to flux up to the top of the boundary layer, you're not going to get any convective activity from it, and that's what's basically controlling the storm size here. Okay, does it make sense?
Yeah. So
So, when referring to microphysics, you spoke about a different type of hydrometeors and how in the different schemes they exchange between each other. You did not speak of how the radiation transfer through them is parameterized.
Yes, I did not. So the question is basically, how is the radiation handled?
Is that relevant? So does it show that
It is relevant, actually. So basically, the simulations, I've investigated this to some degree, and I'm going to try to streamline my answer. But basically, the interaction with radiation depends most fundamentally on the particle size. As the particle sizes get smaller, their interaction with radiation is larger. That's why cloud ice has an outsized influence on the result, okay? Because cloud ice can be formed or can be found in the upper troposphere, right? And because cloud ice has a very large radiative signal because the particle sizes are small. If you have a microphysics scheme that moves mass more efficiently from cloud ice to snow, and some do, like Greg Thompson's scheme, which I use for most of the simulations that I showed here, he tends to produce relatively less cloud ice and relatively more snow. Snow has a smaller radiative signal because the particle sizes are larger. So the way it's working is the microphysics are computing particle sizes. That's being passed to the radiation scheme. The radiation scheme is using that to compute optical depths, okay? And at that point, I have reached the level of my ignorance, okay? Okay?
Yes, very nice, very interesting. The CRF, because the LW is small compared to the MP produced the reading, so they spread from the MP far.
Yes.
I'm wondering whether a different MP would produce a different.
Yeah, but actually, if you remember back to, let me see if I can just go back to my, just remind you what the track plot looks like. Okay. You know, the track plot at right was basically 7 different microphysics schemes. They're still producing different amounts of hydrometeors. Those hydrometeors still have different fall speeds. They still have different, basically, collection and collision efficiencies. They still have different accretion rates. But in the case of this experiment at right, it doesn't matter. Okay? So basically, when I was trying to figure out what's going on, I've got this experiment. I'm trying to do things like, well, what's the difference between this scheme and this scheme? Well, this scheme produces more grapple than this scheme, and grapple falls faster. And you find grapple more in the middle to lower troposphere, and so therefore farther away from the top of the cloud. And at that point, I was still thinking what was going on at the top of the cloud was important because I didn't do that other experiment yet. And so, you know, I was doing things like manipulating fall speeds, and that was having some effect. But, you know, it's kind of like another saying I like is planes need runways, but runways don't cause planes. Okay, right? So in some ways, I was moving the runway around, and it wasn't influencing the plane. Okay, so that's when I decided, well, let's look at some other stuff. And it was certainly a serendipitous experiment that I decided to play around with cloud-radiative forcing. But I have to admit to you that when I turned that term off, I was expecting it to have absolutely no influence whatsoever because a scale analysis suggested to me that it was not important. Okay? Right? And scale analysis is never wrong, right? Or maybe sometimes it is. So,
I wonder, did you look at the cloud-radiative forcing on the system with, say, less lifetime span? For example, like supercell and score lines? Yeah,
I did. And I wrote a paper which I could point to you in which I talked about the influence of cloud-radiative forcing on a squall line. Okay? So basically, what happened there was, it was actually a very interesting paper, very different from this. My deciding to do the experiment turning off the cloud-radiative forcing, I really did expect it to have no influence whatsoever. but it was really motivated by two experiences with very different phenomena, nothing to do with tropical cyclones. So if you don't mind my digressing to explain them, one was the squall line, okay? The squall line, it turned out that with the cloud radiative forcing, the anvil was more extensive. The anvil represents a wave duct, okay? So that gravity wave activity provoked by temporally variable convective activity within the squall line was forcing gravity waves that were able to propagate beneath the wave duct when I had the radiation scheme on, okay? But when I turned the radiation scheme off, the duct went away because the duct was a function of the anvil, and the anvil was supported by the radiative forcing, the cooling aloft and the warming below, okay? What those gravity waves were doing were provoking new convective cells ahead of the squall line. So that was there in that particular case. The other one is, this is a more extensive story. My first PhD student, after he graduated, he and I collaborated on a project. We were using MM5 back in those days, which was pre-WRF. And we were using different versions of the MM5 model to simulate the same case, an extratropical cyclone. And we were getting very different results with regards to the central pressure and how quickly the cyclone moved along its path. It was a nor'easter, so it basically started in the Gulf Coast and went up the East Coast, okay? But I don't remember if it's his storm was deeper and moving faster, or my storm was deeper or moving slower or something like that, but there was a significant difference. We're using two different versions of the model, so I spent several weeks line by line comparing the two different versions and all those subroutines, reverting code from one version to the other to try to see what was causing it. And needless to say, I started with the most obvious things. I thought the boundary layer scheme was going to be really important there, so I reverted all the code changes from the boundary layer scheme, reran the simulation. It made a little difference, but it wasn't the difference that made the difference. So I then did other things and whatever. I finally got to the microphysics, and it was one line of code in the microphysics that was 70% of the difference between his simulation and mine, which was dramatic enough for me to be concerned. One line of code in the microphysics, the fall speed of ice crystals. And I thought, holy cow. Actually, I said something a little more blunt than that, okay? And I would have said it, but someone said they're taping this, okay? Right? And I just thought, holy cow, how did that happen? Right? And it wasn't even a documented change. There were documented changes between those model versions that I reverted, and they made no difference at all. Okay? It was one line of code. And that taught me that, well, many little things can make big differences. Okay?
If you're like me and you have more questions, please join us at lunch. Let's thank Rob again for an excellent Students at 1:45, please join the speaker after lunch.